first one. All right, so the first one, this was the asteroid belt problem. So in this one, it says the asteroid belt circles around the sun between the orbits of Mars and Jupiter. It says one asteroid has a period of 5 Earth years. And remember the period, the symbol for it is T, and it's the amount of time that it takes to complete one full orbit, right? So that's the period. And remember that there was an equation that I'm going to give you on the test, 2 pi r over v, right? Where v is the orbital speed of the object orbiting, and then r is the orbital radius. Okay. Now remember, the period has to be in seconds. So if it's in years, the first thing you have to do is you have to make sure that you convert that. So let's go ahead and convert that real quick. So you have 5 years over 1. Okay, so I'm going to go ahead and convert the 5 years into seconds. Okay, so 5 years multiplied by, I have 365.25 days in a year. Okay. Now, why did I put days on top and year on the bottom? To cancel out the year. Very good. So now I have days, right? Now, I need to get days now into hours. So I have 24 hours in one day. And again, I put the day on the bottom so that that would cancel. Now I have hours. Okay, and then I multiply by 3,600 seconds in 1 hour. Okay, so that's now going to give me my time, my period in seconds. So let's go ahead and calculate what that is. That's 5 times 365.25 times 24, and then times 3,600. So I'm going to get 157,788,000 seconds. So that's how many seconds it takes to for one of those asteroids in the asteroid belt to orbit around the sun once. Okay, so that's my period. All right, so what I can do is I can go ahead and make use of this equation. Let me go ahead and write this in scientific notation. It's going to be 1.57788 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 seconds. Okay, so 1.577 times 10 to the 8 seconds. All right, so I'm going to go ahead and put that in here for the period. So that's going to be 1.57788 times 10 to the 8th is equal to 2 pi r over v. Okay. So now what I could do is I could actually go ahead and just leave it as is. That actually is an equation that relates the orbital radius to the speed, right? Those are the only two variables in that equation, the orbital speed and the radius. Okay. So since we're looking for the orbital speed and the radius, we need another equation in order to solve that for the orbital speed and the radius. So anytime you have an orbit problem, very important that you do this always, is you need to make sure you draw a picture. So we have the sun, and we have the asteroid that's orbiting around, and we're going to assume that the orbit is actually circular. So the asteroid's going to orbit around the sun, something like this. So very important that when you do an orbit problem, that you draw a picture like this, with the force of gravity pointing towards the center of that orbit. Okay. And the next thing that you do is you sum forces, and I'm going to do that over here, sum forces towards the center, and you're going to set that equal to mass times acceleration, centripetal acceleration. So you know that this asteroid is not changing its speed, but you do know that it's changing its what?
Direction.
Direction. As it orbits around, it's changing its direction. Therefore, it has a centripetal acceleration. It doesn't have a tangential acceleration because it's not speeding up or slowing down, but it does have a centripetal acceleration. So the only force that's pointing towards the center is the force of gravity, and that's going to be mass. Now, real quick reminder, this mass right here is always the mass of the object that is orbiting, because that is the one that is actually, that has the centripetal acceleration, which is due to a change in direction. So this is going to be the mass of the asteroid in this case, multiplied by the centripetal acceleration magnitude, which is v squared over r. Okay. Now, can I use, for this force of gravity, can I use mg?
No.
No, we cannot. Remember, mg only works for the force of gravity acting on a body on Earth and close to the sea level, right? This is definitely not at sea level. So what we're going to have to do now is we're going to have to make sure that this is the general equation for the force of gravity. So it's going to be g times the mass of the sun times the mass of the asteroid over r squared. And that's going to equal the mass of the asteroid times v squared over r. Now you notice that one of those masses is going to cancel. Which one's going to cancel? Mass of the asteroid. Very good. Which is the object that is orbiting. So you're never going to actually need the mass of the object that is orbiting because it's always going to cancel in this type of formula. So then you have g. Remember that's the constant that I'm going to give you in just a second. Times the mass of the sun, which is given in the problem, divided by r squared, is equal to the orbital speed of the asteroid squared divided by the radius. Now, very important that you always remember that these two r's are always the same. Okay? So this is the orbital radius squared, and this is just the orbital radius. Now remember, the orbital radius squared is the same thing as the orbital radius times the orbital radius. So if you look, one of these r's cancels with this r. So that means I can go ahead and cancel out that r. So now I'm going to have g times the mass of the sun divided by r is equal to v squared. Okay, so does everybody see how we got this one? Does everybody see that?
Yes.
So now we have another relationship between r and v. So I'm going to go ahead and box this in, and I'll call this equation number 2. Now, if you remember, I also had that other equation that involved the period a little bit earlier. I had period is equal to 2 pi r over v. Okay, does everybody remember this one? Okay. I'm going to do it symbolically, and then at the end I'm going to plug in the numbers. So if you remember me actually putting in the period in seconds, I'm just going to leave it as t for now, and then at the end I'm going to plug in the numbers. So what I'm going to do is I'm going to multiply both sides by v. I'm going to solve for r in terms of v, right? So if I do that, I have vt is equal to 2 pi r, right? And if I want to solve for r, I'm going to divide by 2 pi, right? So I'll have r is equal to vt over 2 pi. Okay, does everybody agree with this statement? Vt over 2 pi. So what will I do with this r now? What can I do with it? Does everybody agree that I can put it in right here for all? Okay. So I will have g times the mass of the sun divided by r, which is vt over 2 pi, is equal to v squared. Now, very important that you know this, that this v will not cancel that one of these v's. It will not do so. Why? Because if you multiply both sides by v to get rid of this v here, watch what happens. That v cancels, but now we're left with v squared times v. Okay. So now we're going to be left with g times the mass of the sun over t over 2 pi is equal to v cubed. Okay. So does everybody see how we got that one? Awesome. Yeah.
Are you doing physics 2 with these?
That's going to be, did I say 3 o'clock?
You said you'd be in your office like 2 to 4.
Okay, so yeah, I can answer your questions in just a little bit because I'm doing just a quick review for the physics 1. Yeah. Okay, so let's take a look. So now we've got, I'm going to go ahead and put the 2 pi up in the numerator. So I have 2 pi, g times the mass of the sun, over t is equal to v cubed. Does everybody see how I got the 2 pi in the numerator? So I have 2 pi g mass of the sun over the period t. Okay, so now, does everybody agree that 2 pi is just a number? Would you agree? What about g? That's just a number. Mass of the sun, that's just a number. The period, we converted that earlier in seconds, so that's a number that's given. 5 years, but we converted it into seconds. So does everybody agree that we will be able to figure out what that is? Okay, so now we just plug in the numbers and we would be done. So this would be like 2 pi multiplied by 6.67 times 10 to the minus 11. Mass of the sun is given, it's 1.99 times 10 to the 30th. And then divided by the period, and the period I gave you over there, 5 years but converted into seconds, 5.778, 8 times 10 to the 8th, and all of that cube root. Now, why cube root? Because this was equal to v cubed, right? So if I want to get v, I have to cube root both sides. So that's the same thing as raising this to the 1/3 power. Okay. So does everybody see how we got the speed? Is everybody good?
Yes.
Now, once I have the speed, what would I do in order to calculate the radius, the orbital radius? Would I have to do all this over again, or is there an easier way to do it?
Should be able to plug it back in
I
somewhere.
should be able to plug it back in. Very good. See this? Radius equals Vt over 2 pi. T is the period. I already know what that is. V, we just figured out right here. So we would be able to plug that in right here to calculate the orbital radius, and then we're done. Okay, so does everybody see how we got number 1?
Yes.
Is everybody comfortable? So remember, if I give you an orbit problem on Tuesday, you will always have to draw a picture like this, and you will always have to sum forces towards the center and set it equal to mass times centripetal acceleration. Always. Then, once you put in your Fg, force of gravity, remember, is g times mass of the object that's orbiting, divided by r squared. And it's equal to the mass of the object that's orbiting times v squared over r. And then you do your simplification, and that will give you a relationship between the orbital speed and the radius. Okay. Then, if they give you a period, or if they're looking for the period, then you would have to use the period equation as well as the other equation. So that'll give you those two equations.